Hi everyone, my name is Márton Braun, and unfortunately with the travel restrictions and everything going on, I couldn't make it to Germany this year. So this is a pre-recorded version of my talk, Decompiling, where we're going to look at how Kotlin features compile to bytecode and learn how some of the things in the language work under the hood. Having already said hi, let's jump straight into it. So we're going to start with a very simple function, and we're actually going to use this simple function for the entirety of this talk. So this multiply function takes two parameters, a string and an integer, and it multiplies the string, by which I mean that it's going to take the string. Let's print the results for these simple parameters. It's going to take the string and concatenate it to itself the given number of times. So with these inputs, we would get hello, hello, hello as our output string. And if you are editing code like this in IntelliJ IDEA or in Android Studio, then you have the opportunity of viewing the bytecode that's being generated from your Kotlin sources. And the way to do this would be to go to the Tools menu, Kotlin, and then Show Kotlin Bytecode. Or you can go through Action Search, which I prefer. So there you would hit Ctrl-Shift-A or Command-Shift-A on a Mac and search for Show Kotlin Bytecode, the name of the command, or some subset of that. And either way, you're going to end up with this panel, which shows up by default on the right-hand side of your IDE, which shows you the bytecode corresponding to your currently open Kotlin source file. Now, if you focus a line in your source, so if you place the cursor on a given line, then you're going to get the corresponding part highlighted in the bytecode, which helps you figure out which part of it is what. But in general, the bytecode isn't super easy to read, so you have to get used to this. It takes a while, and you can kind of figure out what methods and classes are being used and what types there are, but it's pretty hard to track instances and parameters and how things are interacting with each other. So to make this easier, there is a decompile button on the top of this pane, and you can hit this to get a Java representation of the bytecode that you were just viewing. So for this sample, if I were to do that, I would get this Java file in a new window in my IDE. And as you can see, this is kind of the same code as what we have in the Kotlin source and in the bytecode. And the decompiler here is pretending that the bytecode, which was generated straight from the Kotlin source by the Kotlin compiler, is actually an output of compiling Java code. And it's trying to figure out what the original, which doesn't exist, Java code could have looked like. So what we see here is that there is a class wrapping our function. At the bytecode level and in Java, we cannot have top-level functions, unlike in Kotlin. And our top-level function actually ended up being a static function inside this class that was generated. And inside the function, we see the contents that we expect. We see the multiply function being called and its results printed to the standard output, but not before there is a Boolean declared here, which is set to false and then never used. So this is a good point to emphasize that the decompiler is not going to be perfect. You're going to see some odd things here and there in the decompiled output. The decompiled Java code will not always compile as it is. We're going to see some more examples of this later, but it still gives you a very good starting point to understand what's going on in the bytecode. So in this talk, we're going to go through this loop over and over and over again, going from Kotlin source files to bytecode in class files and then decompiling that back into Java code. Most of the time, you're just going to see me go straight from Kotlin to Java. But remember that there's no conversion like that. We're actually going through the bytecode and then decompiling it. All right, so we have this very simple function, and I assume that anyone watching this talk could implement a function like this. And I'm going to do that now. So I'm going to start with the most straightforward implementation that I could come up with. So I'm going to declare a string that's empty to start. Then I'm going to loop the given number of times. And in each loop, I'm going to concatenate the input string to the result string. And at the end of the method, I'm going to return the result. So this is our first implementation of the multiply function. And now I'm going to run this through the compiler and then the decompiler, and see a Java representation of its bytecode, which looks like this. Since this is our first sample, we're going to go through this line by line. starting with the header of the function. So we have a top-level Kotlin function, just declared in a file, not wrapped in a class of any kind. and we can see that this resulted in a static function being generated in the bytecode. This means that we could call this function from Java code if we wanted. We just have to reference the correct class and then call this static method inside it. Inside the signature, we can first look at the return type. So the return type in Kotlin was a non-nullable string. So in Java, this is a string, and it's also annotated with not null to indicate that it's not going to be a null value. And the same goes for the first parameter of the function. Again, non-nullable string, it's annotated with not null. Moving on to the second parameter, which was an int in our Kotlin code, we can see that this is a primitive int in the bytecode. So the reason why the compiler did this is because it could, since we are not accepting null values in our Kotlin code, it can use a primitive type. And this also doesn't require an annotation because a primitive type cannot hold, just technically cannot hold a null value anyway. If we were to do something like allow a nullable int in our Kotlin source, then we would see a integer, a boxed reference type integer in our bytecode, and it would be annotated with the nullable annotation. Going to the first line of the method in the bytecode, we see that there's one more thing here which actually belongs to the signature of the method. And this is a call to a method inside the intrinsics class, a static method inside this class. And we're passing in the first parameter of the function as well as the name of the first parameter as a string. So since this is a static function, Java clients could call this multiply function, and the Java compiler does not respect the nullability annotations placed here. So even though we have a not null annotation on the first parameter, the Java compiler would allow you to compile bytecode, compile Java code that passes in null as the first value here. The Kotlin compiler would catch this and give you an error, but you can compile things from Java that would pass in null. So in order to prevent the method from getting somewhere halfway and then crashing in an unexpected way with a null pointer exception, the Kotlin compiler injects this kind of intrinsics check in the very beginning of the method. And if we navigate to this, which we can do in our IDE, we're going to find the intrinsics class and the method inside it in the Kotlin runtime. And you can see that the method is actually just a null check. And if it does fail the null check, then it's going to delegate throwing the exception to the next method of the class, which grabs a couple of things from the current stack trace, as well as the parameter name that was passed in as a parameter. And it gives you a very, very nicely formatted exception message, which tells you exactly what failed and how. So it's going to tell you that there was a problem with a parameter being null when it shouldn't have been, and it's going to tell you the exact class, the method, and the name of the parameter that was problematic. Great. So after this check, we actually have the body of the method, and there aren't many surprises here. We see the empty result string being declared, and then whatever is in it returned at the end of the method. And between the two, we see the for loops implementation. The indices are being used in a weird way, and the variables as well. It's not what you would write in hand in Java, write by hand in Java, but it does what you expect it to do based on the Kotlin code. So not much to look at there. Okay, let's start iterating on the multiply function, which we're going to be doing for the entire talk. So the first thing I'm going to do is I'm going to take the first parameter of the multiply function and pull it into a receiver in our Kotlin code. So instead of having to call the multiply function and passing in two parameters, we're going to be able to call the multiply function on a string and then pass in just one parameter afterwards. If we go ahead and decompile this new function, we're going to see that very, very little changes in our bytecode. So all that changes is the name of our first parameter, which is now $this, $multiply, indicating that this is a receiver. This is a this in some scope, and it's in the scope of the multiply function. So two things we learn here. One of them is that a receiver of a function is actually just a regular parameter. So all of the parameters in this case shift over by one, and then the receiver becomes the first parameter at the bytecode level. And two, that extension functions, if they are top-level functions, are simply static functions, just like any other top-level function in Kotlin. Now I'm going to reformat the header here so that all of the keywords that Java requires can still fit on the slide. Since extension methods are static, they have some significant differences compared to regular methods of classes. And let's take a look at this when it comes to inheritance. So here's a very simple example where we have an animal class that's able to identify itself as an animal. And then we have a more concrete implementation of an animal in the form of a cat, which can identify itself as a cat. So if we store a cat in a reference which has the type animal, as you can see in the main function here, then we expect that calling the identify method on this reference will actually run the code inside the cat class, which prints this is a cat. This is one of the basic ideas for our object-oriented languages, and this is what makes polymorphism possible, a feature called dynamic dispatch, which will decide at runtime which specific function to call when functions are being overridden in a class hierarchy. So what if we pull these methods, instead of having them inside the classes, what if we pull them out into extensions? So now I have two empty classes. Cat is still an animal, but both of the identify functions are defined as extensions on the two types that we have. Well, if I were to run my main function again, I would now get a different result. So this time the identify function defined for an animal is what's being executed because extensions are static. This means that we can't wait until runtime to decide which one we're going to call based on what kind of actual object is stored in the animal reference. Instead, we have to pick the most fitting one for the type of the reference, which is animal, at compile time statically. So we pick the one that's defined for an animal, and we get this as an animal. So remember that you can't override extensions as you would regular methods. All right, the next thing I'm going to improve here is this line of the Kotlin code. So if I had this code in the IDE, I would have a warning on this line by now, which would be telling me to simplify it into this syntax. So instead of having the long form concatenation and then reassignment of the value, I can use this plus equals and a single operator. If I were to decompile my code at this point, I would be looking at the exact same thing that I had before. So nothing changes by me refactoring this in Kotlin. We still have a Java-style concatenation in our bytecode. But let's discuss how exactly Kotlin's operators are translated into function calls in the bytecode. So let's take a look at one of these compound assignment or augmented assignment operators. First, the compiler is going to look for a method with a corresponding name, for example, plus assign for the plus equals operators. And if it finds a method that it can call on whatever A is and accepts a something that's of type B, then it's going to pick that method and place that function call into the bytecode. If these methods don't exist, which is the case for our string concatenation, there's no plus assign method on Kotlin's string type, then it would unroll the expression into its longer form and then look for the corresponding operators again. And this is where we get a match with our strings. So the plus operator as a function does exist on the Kotlin string type. So that's what we're getting after it's unrolled during compilation. And that plus function for strings is corresponding to the Java plus symbol for concatenating strings, the plus operator rather. Cool, so we have a multiply function and it works well enough for what we need. So now I'm going to start refactoring this and extracting some of the logic in it. The first thing I'm going to do is introduce a method called repeat, which is able to perform a given task a given number of times for me, so that I don't have to implement the for loop myself inside multiply. So if we adapt multiply to this, then I can replace the for loop with a repeat call, pass in the number of times, and then pass in the action I want as a lambda, like so. Let's decompile the repeat function and see how it works. The interesting part here is going to be how functions are handled in bytecode. So the second parameter of my repeat function is a Kotlin function type that takes no parameters and returns unit, so it doesn't return anything. And this in the bytecode is a function0 object, which we can see as a reference type because it's annotated with not null and it's being checked at runtime to make sure that it's not a null value. And whenever I call the function in the Kotlin code, we can see that that corresponds to a call of the invoke method on the function0 object. The function0 type is again something we can navigate to in our IDE very easily. So I can go to the definition in the Kotlin runtime and see that function0 is an interface, which is supposed to represent a function that takes 0 arguments, and that it only contains the invoke method that we saw being called in the bytecode. There are additional interfaces for functions that do take parameters. So for example, function1 takes an extra type parameter, and then its invoke function takes that type as its single parameter. And then there's function2 and function3, and this actually goes on for a while, and then it goes on for a little bit more, all the way up to function22. So that would be a function type in Kotlin that has 22 different parameters. And so these are being used in the bytecode up to 22, and you can actually go up to 255 parameters with a Kotlin function type. That's a limit defined by the JVM. But after 23 parameters and more, you're going to see a different implementation in the bytecode, which I'm not going to cover here, but I encourage you to define some functions like that, decompile it, and try to figure out how they work. Okay, so that's the definition of the repeat function, which takes the function0 as its parameter. Now let's go to the use site, so to the multiply function, and decompile it to see what using the repeat function and passing in this function0 looks like in the bytecode. And if we decompile the multiply function now, we're going to see that it got very, very complicated compared to what we had in it before. There are some expected parts here. So we see the repeat function being called, a int being passed in, and then a function0 being defined as a anonymous implementation inline here within the multiply function. And inside it, we have a invoke method being implemented, and that's what contains the code of the Lambda. However, we also have a bunch of other things here. So we have something called an object ref being created and replacing a string inside a field in it. Then inside invoke, we have a lot of manipulation of variables back and forth for some reason. And then the end of the method is kind of complicated too. We're grabbing something out of this object ref result thing. It's not straightforward. So what would we have done if we were writing this code in Java by ourselves? Well, we could have defined an empty string to start with, and then return that string at the end of the method, just like we had before. And then inside the function we're passing into repeat, which will be executed a bunch of times, all we really need to do is grab our current result, concatenate the receiver string to it, and then reassign this to the result variable. We have a couple of problems here though, which is why the Kotlin compiler didn't generate this code. So the first problem would be right here, when we first try to reference the result variable inside our Lambda. So since we're in a inner class, in a closure of sorts, here we cannot reference variables that aren't final. This is a limitation of Java. So in order to have access to this result variable, we have to make this a final reference or final local variable in the multiply function like this. But now we have another problem, which is we can no longer reassign the result variable. So string concatenation creates a new string instance because strings are immutable on the JVM. And what we want to do here is make the result variable point to this new string instance in memory, but we can't do that if we've marked it final. So we have this catch-22 situation where we need this variable to be mutable so that we can update it, and also we need it to be final and non-mutable so that we can capture it in our Lambda. Putting this visually, this is what a non-final reference would look like. So this is a reference to a string which we can update, and we can make it point to new instances. And then I'm going to illustrate a final reference like this. So this will always point to the same string instance from the time it was first assigned and forever. Going back then to what the compiler generated for us, we have this object ref being used, which we have to demystify. So let's again just simply jump to its definition and see what it does. So an object ref is a very simple generic class, and all it does is it holds a reference inside it. It has a field inside it to whatever type we want to reference. So what's being done here is that we're creating an object ref at the beginning of the method and replacing an empty string inside this object ref. So object ref really is just giving us an extra level of indirection here. So it's kind of like a pointer, or you can think of it like a box that we're placing a value in. And we're always going to have the same box. So our object ref is final and we can reference it inside our lambda, but we can grab the value out of it. That's the second line in the middle of the function. And then we can modify that value and place a new value, the reference to our new string, back into the object ref. And finally, at the end of the method, we're just grabbing whatever we ended up with inside the object ref. Going visual on this, hopefully that helps with the explanation. What we have here is a reference to object ref, which is final, and it's never going to change because we're always going to have that same box to store a reference in. But the reference inside that can be updated, and we're going to keep updating that as we're going through the different loops over and over again as the repeat function is being executed. Great. So now we have this function 0 that needs to be created every time that we call the multiply function, because each of these function zeros has to operate on a different object ref instance. So there's allocations happening every time we do this, and there's a new function 0 being used. What if we had a simpler function passed into repeat, which doesn't require any external parameters? Let's take an example like that. For example, this super easy, super simple function, which just prints a hard-coded string. So if I were to decompile this with the built-in decompiler of the IDE, I would see something like this in my Java code, which doesn't really make a lot of sense. So we have this null.instance here, which is probably nonsense, maybe doesn't compile, maybe it's a null pointer exception at runtime. It's definitely not sensible Java code. So this is a good example of a limitation of the decompiler that we get in the IDE. So if you have a function that doesn't capture any values, it has a hard time decompiling the bytecode of that for whatever reason. So to explain what's happening here, I had to grab a separate decompiler. My favorite for simple things is JetX because it's just very easy to use. And with that decompiler, we can actually figure out what happened here. So we would find a function 0 implementation, so a class that implements function 0 in our bytecode. And inside its invoke method, we do have this print statement that prints a static string. And we would also find a field inside this class, which is called instance, and it's static, and it contains an instance of the class that it's in. So this is a basic implementation of the singleton pattern, a class containing a single static instance of itself. And this is what the null.instance we saw earlier was meant to reference. So this is actually an instance of this generated function implementation, which is used every time that we call the example function that we have. So because we are not capturing any external values, we can just reuse the same function 0 instance and don't have to create newer instances as we go along. Okay, getting back here. So we're doing all of these allocations. We're creating these object refs, we're creating these function zeros and so on. What if we could avoid this? What if we could extract logic from our multiply function and didn't have to pay the costs of creating objects and calling functions and so on? Well, if we go to the repeat function, we can do something that does just that exact thing for us. This is a feature of Kotlin. And all we have to do is mark this function as inline. If you change the repeat function, if you want to see what the effect of that change was, you probably want to go and decompile the repeat function. But if you do that, you'll actually find that it didn't change at all. So it's the same as it was before. But if we go to the use site and take a look at what the multiply function's bytecode looks like, then we're gonna see some significant changes. So this is actually the correct decompiled result of the multiply function. I didn't go back to previous slides accidentally, but what we see here is that there is no call to the repeat function, there's no function instance being created, there's no object ref being created, none of that. All that we have in the multiply function's bytecode at this point is creating the string, having the for loop right there in the body, and then returning the result. So this is the optimization that inlining does for us. It takes the contents of the repeat function and it places them inside the multiply function so that we don't have to actually perform a function call there. Let's take a look at this more visually. And even though this transformation happens on some intermediate form of the code during the compilation process, we're going to go into this like dream scenario where this happens on the Kotlin source code so that we can track the steps of it more easily. So the way to think about inlining is that whenever we call the repeat function, and this is done separately for every usage of repeat, the compiler would take each of its parameters and substitute the concrete value that's being passed in as that parameter. So for example, the first parameter here is times, and we're passing in a local variable called times into the function. So we would place that to every occurrence of the parameter in the repeat function's body. And the second parameter is a function type, which is being fulfilled by a lambda. So we would take that lambda and place it to wherever action was being used. And since we are calling that lambda immediately, we can just have the body of the lambda right there instead of creating it and then calling it. After substituting each parameter of the method that we're inlining, we can simply take the body that we have with all of these substitutions and replace the original call to the method with it. So this is how we ended up with all of the looping logic inside the multiply function at the bytecode level. So this is great. We have free abstraction. We are extracting logic from the multiply function, but we're not paying any costs for it at runtime. Now, let's take a look at this line again, which we've discussed before. So we know that this operator will translate to a Java-style string concatenation with a plus operator under the hood, but this is going to be the one time in this talk where we actually look at the bytecode to figure out what that means. So a Java concatenation will actually be a string builder usage in the bytecode if we look close enough. And in this bytecode, you see that there's a string builder being allocated in memory. Then its constructor is called. That's the init call on the string builder. Then we call append on the string builder twice. And finally, we call toString on it to grab whatever string we've assembled inside the builder. And that's what we're returning and reassigning to result. Putting this visually, what's happening is that whatever string we have as our current result, we're taking the input string, we're creating a new string builder, so allocating a new array of characters in memory, and moving both of these strings into that new place in memory. And then as we go around and go to the next iteration, we're gonna again allocate a new string builder and move both of the string inside it, and so on and so on. So for every step of the way, we have to create this new string builder instance, which we append things to, and then we extract a new string from it, and then we throw away the string builder and we have a new string instance. All of this allocating instances and moving things around in memory is a very costly operation. So we could do better if we were writing more precise code ourselves. Let's do that then. Instead of using strings, we can use the String Builder API ourselves. So we can start with a string builder at the start of our function. Then we can append the input string to the string builder over and over again. And finally, just grab the contents inside the string builder and return that from multiply. If I decompile this, I'm going to see things that I expect. So there's the creation of the string builder with a constructor call. There's append calls inside the for loop. And at the end of the function, we see something interesting. So the builder.toString expression isn't being returned directly. Instead, it's saved into a local variable first, and we're passing in its value into another intrinsics call. So this call is injected here because we are promising in the Kotlin code to return a non-null string, but String Builder is a Java-based API. So when it tells the Kotlin compiler that the toString method is going to return a string, the Kotlin compiler cannot be sure that that's going to be a real string instance. It might just be a null value. So to avoid breaking the contract of our function and accidentally returning a null, the compiler injects this intrinsic null check here, and it will just throw an exception instead of returning from the method if the Stringbuilder API doesn't behave nicely. You may also spot that the expression itself that's being returned, so builder.toString, is being passed in as a string into this intrinsic check. So if this somehow fails, you can of course expect a very nicely worded exception message. Okay, so we have this pattern of using the string builder, which is a very common pattern when working with this class, where we are creating a string builder instance, we're appending things to it for a while, and then we're extracting the value from it. And we can extract this logic of using a string builder like this into a separate function again. So we can define a function called buildString. Inside this function, we are creating a new string builder instance. Then we're performing a bunch of actions on it, and then we're returning the string that was assembled in the builder. The actions that we're performing are defined in a lambda. So we're taking a lambda as the parameter of buildString, a lambda that's an extension on the string builder type, so that whoever's implementing the lambda can call methods on a string builder. And that string builder is going to be the one that was created in our buildString function. So let's update the multiply function at this point, and instead of creating a string builder there, we can just use buildString and then nest the repeat call into it, and then append the input string to the string builder that we had. So the reason that I can call append within the lambda being passed into buildString is because that's implicitly calling it on the string builder. That's the receiver of the builder action lambda up there. But now that we've clarified this, we might also notice that I've introduced a bug at this point. So I'm now appending the string builder to itself by having written down append this, instead of appending the receiver of the multiply function. So to fix this, I would have to be more explicit and say that what I want to append is really the this reference at the scope of the multiply function. Please note that this is here for educational purposes. So if you find yourself having to juggle between different receivers this much, you might want to consider not nesting this many things inside each other. But this is the way that you can disambiguate between multiple receivers if you really have to at some point. Great, so now we have this new implementation for multiply. Let's decompile it and take a look at how the buildString call works internally. Looking at the buildString call, we see a function being passed in, which is good. That's what we expect now. And this function is a function 1. Even though this function doesn't take any parameters, it does have a receiver, which we now know that is actually the first parameter of a function. So that's why we're using a function 1 and not a function 0. And we can also see this in the signature of the invoke function. So we see the string builder, the receiver, being passed in. It has the conventional name of $this, $buildString to indicate that that's a receiver. Inside the method, we see some intrinsic checks. We see the repeat function being inlined here. So that's where the for loop comes from. And then in the very middle of all of this, we see that we're appending one of the receivers to the other one. And again, the bytecode is very nicely readable here because we have these well-named receiver values. At this point, we are gonna optimize some more. So we've again extracted some logic, but we're paying the cost of having to allocate this function 1 instance every time. So to avoid that, we can go to our buildString function, and just like we've done for repeat, we can mark it as an inline function, and that would simplify our multiply function down to this final form. So now we have a multiply function which contains both the string builder's creation and usage, as well as the looping logic, the repeat logic inside it directly, without having to create any function instances or anything like that. So we have very performant bytecode. However, if we take a look at what we have in our Kotlin sources now, we can see that we have extracted multiple pieces of reusable logic, which we could then use in other pieces of our other places of our code base as well. With that, I'm now going to tell you that you shouldn't be writing functions like this. But the only reason I'm doing that is because both of these functions are part of the Kotlin standard library. So you'll find both repeat and build string inside the Kotlin standard library in different packages. And both of them are actually going to be implemented better than what I've done here with my own implementations. So for example, the repeat function takes an extra integer as a parameter for the lambda that you pass in, so that you can use the current index of the iteration if you need it for something. And it also has support for Kotlin contracts to make sure to enable you to use it in more scenarios. So you would actually be able to just get rid of both of those helper functions and use the built-in ones like this. Now we have one final thing to address here, which again is a question of performance. So the build string function uses a string builder under the hood, just like I've shown you. But a string builder still isn't a magic solution for never reallocating memory. So inside the string builder, we have a character array of some size. And whenever we fill it up with characters, it has to allocate a new array and move everything over to that. This is much more efficient than creating new string builders and new strings on every line, but it's still memory reallocation that we could have avoided. And the way to easily do this now that we're using standard library functions is to use an overload of the build string function, which takes the initial capacity of the string builder to use. So since we know the exact size of the result string that we're going to have, we can just calculate that using length times times and pass that in so that the string builder is immediately allocated to the correct size, and that array is just being filled up as we're progressing through our repeated loops. Okay, so that's all I had for you today. I want to point to a couple talks that have already covered this same topic, because of course this isn't a very original idea, because nothing ever is. So the first talk I've seen on this topic was by Victoria Gonda back in 2017. Then there were a bunch of other talks. So there's a talk by Yonut Belosin from last year, where he goes more into benchmarking and concrete hard numbers on the performance of certain Kotlin features. This is definitely worth watching. Then there was a talk by Chet Haas and Roman Guy last year at Google I/O, which discusses mostly modern Kotlin features and how they work. And then even more moderner Kotlin features were covered by the same two people at last year's Kotlin Conf. So all of these videos, all of these recordings cover different features than what I've shown you here today. So if you're interested in this topic, you can either go out exploring on your own, or you can take a look at some of these and have more of a guided tour to some of Kotlin's features. And with that, I would like to thank you for attending this talk. If you want to follow me on Twitter, that's my username. I post things about Kotlin and Android mostly. You can also reach me there if you have any questions. And if you want to grab either the slides of this talk or look at some of the resources I've mentioned, or even more, for example, the JetX decompiler and things like that, you can go to my website where you'll find all of that info on my talks page. And this is where I would usually ask for questions, but we're going to skip this again. Please use those links and references to contact me if you have any questions about this talk. And once more, thank you very much for attending, and have a nice Kotlin.